So now we have finished data estimation, planning, and control. Means that we're doing learning now. It's exciting. So we'll do learning, we'll do imitation learning today. Next class is seated discussion, and we'll have a guest lecture on Friday. And we'll get back to reinforcement learning on Monday and Wednesday, and then we'll have our last seated discussion next Friday. And that's the end of the quarter. All right. So let's start with our little quiz. Why is RRT star referred to RRT? Prove little guarantees, speed, optimality. 10 seconds. And got the answers in? Okay, let's keep going. It's because of optimality. RRT star gives you more optimal paths than RRT, which are shorter and smoother and so on. Okay, so where are we in our journey to build a robotic system? We've gone from sensors to actuators through this combination of state estimation, world modeling, planning, and control, right? So world modeling is just a physics model. State estimation tells you where your robot is in the world. Planning tells you a global plan of how to get through big parts of space. And then control tells you how to follow waypoints in the presence of disturbances and noise and inaccuracies in your model. Right? And so we've this is what you call model-based control. We've kind of built a system for model-based control because it relies on a known physics model of the world. And so this is what robotics has been for the last 70 years. And what most robotic systems in industry currently use. They use this model-based system of state estimation, planning, and control. And that's how most production systems work. And so we've described how to build most production systems. Are we done? I think the answer is no, because we're at a unique point in history where I think a lot of robotic systems are moving to learning-based systems. And it's an exciting time to learn about robot learning because it doesn't quite work. It doesn't quite work yet, but it will in like 2 years, and it's starting to show signs of working. So model-based control for robotics typically has a pipeline that looks like this. You go from state estimation to modeling and prediction to planning to control. That's what we've studied so far, right? And each of these modules have like a fixed interface between them. State estimation outputs a belief state, modeling outputs the next state, planning gives you waypoints, then control gives you torques, right? And what the learning-based approach to robotics looks like is it takes this whole pipeline, which has been so beautifully designed, and it says, let's kind of change the paradigm, go end to end, right? It says, let's take a big ass neural net, let's take in perception with output control. And the answer is not always as simple. You often have to design what the interfaces are still. You still have to choose what your actions are. You still have to choose a representation of your input. So it's not like a trivial problem, but in general, what end-to-end policy learning does, it takes the approach of not building these modules step by step by step, but rather just optimizing for the problem we care about, which in this case is control, right? And saying, let's take a data-driven approach to robot control, and let's try to collect a bunch of data and try to learn a policy that goes from a policy as a controller that goes from perception to action. So kind of your big neural net subsumes state estimation, it subsumes planning, it subsumes control into like a single large model. Right now, like within end-to-end policy learning, there's like different architectures you can use. There's different like specific algorithms, but generally it's shifting the burden from human knowledge to data. And the hope is that as you get to systems that are harder and harder and harder to model, like you go into home, it's hard to model everyone's home. You scale better with data than you do with human effort, right? And so that's kind of the premise of going from a model-based system to a data-driven system. What are some cons with doing that? Like we talked about this at the start. You lose interpretability, right? Other cons. Data collection can be very expensive. Yeah.
If the data is collected like in simulation,
Right. So like collecting data in simulation is an interesting thing because it's kind of like it's model-based-ish, because where you're getting your data from, you're getting it from your model. Whereas like end-to-end is often in the real world where you're collecting data from the thing you care about. but it's like in between. But it's nice because the data is cheaper, but it's wrong a little bit, right? Other cons. Right. But inherently, models that humans design are meant to generalize. That's kind of what physics is. Whereas machine learning models are often quite fragile. And so physics models extrapolate a lot better, that are more, they don't capture the nuances in the same way, whereas end-to-end models will capture the nuances but don't often generalize, right? But the bet is that this thing gets better as you have more and more and more data. And so the longer you deploy your systems, the more you expect an end-to-end system to be better. Okay? And so what we're going to study today is we're going to start by defining a formalism for sequential decision making and like learning-based control. We'll then talk about an algorithm called behavior cloning, which is a basic version of imitation learning. We'll talk about some fixes to problems in behavior cloning, and I'll show some cool videos at the end. Right? Alrighty. So the framework that you typically use for sequential decision making is something called a Markov decision process, or an MDP. And a Markov decision process has states S, actions A, rewards R, and transition dynamics P. And so we've seen some versions of this throughout. We've seen states and actions before. We've seen rewards in terms of costs for optimal control. And transition dynamics is kind of like your world model, right? But an MDP is called an MDP because of the Markov property. We've talked about the Markov property before too. So the past is independent of the future condition on the present, right? And we can start that way. So it's kind of the same formalism we've been using thus far. The difference is that what we've often been looking at is a form DP. So in an MDP, you're going to assume that the state is known to you. You're going to see the state. You're going to see the state. Whereas in the things we've looked at, we only see observations, right? So if you remember all of our Bayesian filtering stuff, you like only see observations, right? And so you have to do this like state estimation stuff. So the simplified model we're going to consider for the next few lectures is MDP, where we're going to assume the state is known to you, but the model of the world is not. And so it says that we don't know this, but we do know this, we do know this, we do know this. Right? So it says states, actions, and rewards are known. You don't know what the model of the world is, which means you can't you don't have a simulator of the world, but you can draw samples from the world. So you can like execute things in the world, you can draw samples, you can try things, but you don't know what the model is. You can only get data from it. And so that's the setting we're going to think about. That makes sense? Okay, so in that setting, we're going to define a trajectory as a sequence of states, actions, rewards, states, actions, rewards, states, actions, rewards. Okay? And the important thing in a Markov process is because the present is enough to make decisions, you only need to know the current state to make an optimal decision. You don't need to know the past. Okay, so that's the MDP. Pretty standard. Questions? Okay, let's go from the MDP. We can instantiate this for a kitchen. So for instance, in the kitchen, your state is going to be things like your camera images, your joint encoders. Your actions will be things like your joint torques or joint velocities on your arm. Your reward might be things like how you're trying to put the kettle into the sink. It's like how far is the kettle from the sink? And then your transition dynamics here are just physics of the world, right? Like how does your robot transition? How does it make contact with objects? It's unknown, but you can get samples from it. Okay, so given that formalism, what we're trying to do in reinforcement learning is we're trying to reinforcement learning, imitation learning in all of these cases. You're trying to learn a policy by theta that takes some state SC, gives you action AT. Right? So it's essentially a set of rules that takes in a state and tells you what the action is. And it's called pi theta, pi sub theta. Theta is called the parameters of your policy. It is the things that like determine how your rule book behaves, and pi is called your policy. Right? So it's like some function approximator, like a neural net, like a table, like a linear model, like a decision tree. It can be any of those things, but something that takes in your state and makes a decision about what action to take. Right? And to what end you want to decide what action to take so that you can maximize the expected sum of rewards. Right? This is a typo. It should be expected sum of rewards, not the sum of expected rewards. But the goal here is that you want to figure out how to act in the world so you collect as much reward as possible. And the reason it's expectation is because your policy can be stochastic. It doesn't have to make decisions in a deterministic way, and your environment can be stochastic, right? And so you want to say that what is the best thing to do on average, right? And your goal in imitation learning, in reinforcement learning, all of that is to basically determine these parameters theta, which find you a strategy that maximizes the expected sum of rewards, right? And so the expected sum of rewards is often written as this. It says that if you sample trajectories from your policy pi theta in your environment, then you want to collect as much rewards as possible, right? So you say over t time steps, you're going to sum up your reward. You're going to average it over trajectories collected from pi theta under your environment p. And you want to choose the theta, which gives you the best average, right? So it's like try to find the strategy that gives you the best possible expected sum of rewards. Right? So almost all reinforcement learning and imitation learning and all of this stuff just tries to solve this objective through different approximation. Yeah. And so that's the objective we're going to try and solve. Remember, we're going to assume that R is known to us. We're going to assume that we're going to like sample things from pi theta and p. P is our dynamics and pi theta is our policy. We're going to choose the class of our policy, but we don't know what theta is, and we're going to try and figure out what theta is through experience, right? And so as you're doing trial and error in the environment or in imitation learning, you're learning from an expert, but you're always trying to figure out what theta is. That's the problem statement. Okay. So with that in mind, let's ask, why isn't this optimal control, right? It sounds exactly like optimal control. And there's some differences, right? So the primary differences between optimal control and reinforcement learning is that optimal control assumes the model is known. And reinforcement learning assumes that the model is not known, but you can draw samples from it. And there's other things, is some things are minimizing cost, some things are maximizing reward, some things are continuous and discrete time. Those things don't matter as much. Like the main thing that matters is you assume that the model is known or not known. Okay? And so like whenever you hear model predictive control, typically it means optimal control when you know the model, at least approximately. And reinforcement learning, you don't know the model, but you can take samples from it. And optimal control, you don't usually try to learn parameters, whereas in reinforcement learning, you do. Yeah. Oh, you're just stretching? Okay. Okay. So the main thing of interest is a policy, right? So policy is a mapping from states to optimal actions. And so the first version of things that people did is they just made a big ass table and they put states and they put actions in the table, and that is your policy, right? And you use like a hash table, feed in states, you get action, the policy. And so a lot of reinforcement learning theory looks at this setting, which is tabular, right? You can go from tabular to something that is slightly more complicated, which is saying you're going to choose actions according to something that's linear, right? So you'll have some features of your states and actions, and you'll have something that's linear in those features, and that is like your dependence between your states and your actions. But what lots of people are using in practice now are a lot more complicated function approximators. So things like neural nets that take in images and output actions, or decision trees, or things like that. A lot of what my group and a lot of robot learning people focus on is neural net function approximators and how do we learn them from data. Okay, so there's different ways we can kind of go about this. The first is, I guess we're going to go this way, but imitation learning is when you're trying to learn these policies from expert traces, like an expert gives you some data, try to learn these thetas from data. Another way of doing it is model-free reinforcement learning, which is like learning through trial and error. You just try things in the world, see what works, see what doesn't work. And model-based RL is trying to build a model of the world. So trying to build an approximate understanding of how the world works and then plan in your imagination, right? And so model-based RL is very much like optimal control. It's just with a model that you learn from data, right? Model-free RL is very much like, if you've heard of like Pavlovian experiments, like you have a dog and you like ring the bell and it responds to stimulus. It's very much like model-free RL. You try things, do trial and error, do things that work better more, do things that worked worse less. And imitation learning is very much like copying the teacher or a parent, right? And so those are the three things we're going to try and cover, if I can go fast enough. But we'll start with imitation learning. Yep. All right, so let's go through imitation learning. Imitation learning is hot shit right now. There's like hundreds of millions of dollars going into imitation learning. And so it's a good thing to know. But we're going to start with imitation learning. We'll talk about why it's not perfect. And then we'll talk about some fixes that people have looked at in recent years. Okay, so the key idea behind this kind of imitation learning algorithm, which we call behavior cloning, is that you're given demonstrations of optimal behavior. So you're given a set of demonstrations. Let's say it's like S, A. You're given n tuples of S and A, right? Where S is a state and A is an action from an expert, right? So if it's a car that's driving, it's going to be images from the car and then like actions of the steering wheel and the throttle. A question mark? Yeah. Have a model. What is model-based? Yeah, so when you say model-based reinforcement learning, so the assumption in all of these is that a human doesn't give you the model. A human just gives you access to the environment. And so what model-based reinforcement learning does is it says, let's just collect data in the environment. Let's try to like learn a model of how the world works and then pretend that that model was like our optimal control. So like the eventual methods that you develop are very optimal controlling, but with the fact that it accounts for the fact that your model is learned and might have issues. I don't know. Good question. Alrighty. So the idea here is we're given some traces of states and actions from an expert, and your goal is to try and train a policy that can mimic what the expert did, right? And so you're given states and actions. These are assumed to come from an expert, right? So let's call it pi star, right? And we don't know what pi star is. We just know what traces of states and actions are from pi star. We're trying to use this through our imitation learning procedure to get pi theta, right? And we want pi theta to like copy the behavior of pi star as much as possible. But all that pi theta sees are states and actions that pi star executed, right? And so the idea behind behavior cloning is to treat imitation learning as a supervised learning problem. How many of you have heard of supervised learning? Mostly? Okay, so supervised learning, for the large part, is what you call maximum likelihood, right? So the idea in supervised learning is, let's say you have a data set of X and Y, right, from something that's an expert, right? What you try to do is you try to learn, say you sample X and Y from your data set, you try to learn a P theta, which maximize the likelihood of Y given X. Okay, let me rewrite that, sorry. X and Y coming from your data, log P theta of Y given X. Okay, so what it's saying is let's try to figure out the parameters of theta, which maximize the likelihood of the function producing Y when it's input X, right? So saying that if I was at X, try to increase the likelihood of Y. And so P of theta, remember, is a probability. It's going to be like a probabilistic function. And you're trying to say, let's try to maximize the likelihood of producing Y when you feed an X, right? And you're going to take this objective and you typically optimize it with gradient descent, right? And so if P of you can choose different forms of P of theta, but if P of theta is a Gaussian, then this becomes a regression problem. If P of theta is a multinomial distribution, this becomes like a classification problem, right? And so essentially different choices of P theta give you different algorithms, but all of them are just trying to do maximum likelihood. You're trying to maximize the likelihood of Y being produced when you input X. Right? And so in our case, what we're going to do is we're going to try and maximize the likelihood of, we're going to take all our trajectories from our expert. We're going to like convert them into state action tuples. We're going to pretend that you had independent state action tuples. And then you're going to try and maximize the likelihood of producing A when you feed in S. That's it. Right? So imitation learning with behavior cloning is the like silliest possible thing you could do. It's just converting expert trajectories into IID samples of S and A. And then you're just going to try and maximize the likelihood of your policy producing A when it's fed in S, right? And this only works because you said that the data was expert. Said the data was non-expert, this means like you're copying a non-expert, which doesn't really make sense. So that's the whole idea of behavior cloning. So it says that you're trying to maximize the likelihood of producing A star when you get S star, right? So the important thing is you like take all your data, you mush it into these tuples, you pretend they're IID, and then you do maximum likelihood, right? So that's what a supervised learning problem is. It's what you do for classification. It's what you like in the classification, you would take in an image, go through it, produce a class, right? Is it a tiger or a cat or a plane or a dog? In this case, we're just going to take in an image and produce, do you go left, do you go right, do you go straight, do you go diagonal, do you go backwards, right? And so you can choose different forms of phi theta that'll lead to slightly different algorithms, but all of them are basically take the simplest version of supervised learning in PyTorch and you can implement behavior cloning. It's very easy. Okay. So this is kind of the whole code for behavior cloning. It's like 30 lines of code. If you do this, then you get hundreds of millions of dollars. So that's great. But if you look at this code, it's essentially just supervised learning, right? So if you look through this code, it's just saying like you're gonna like sample a batch of data, you're gonna like predict what the action was, and then you're gonna try and like maximize the likelihood of it, right? There's like nothing much to this data, just nothing much to this code, it's just shuffling data and then just doing maximum likelihood. And depending on your policy class, if it's discrete, you'll do classification. If it's continuous, you'll do regression. Okay? But that's basically it. And so the first time people did this was back in 1989, I think. And so they were driving this car around. I think it's called Alvin. And so this was the input. And it went through like a simple one layer neural net, and it kind of predicted whether you go left or right. And so actually, I mean, those are videos of this thing actually navigating. And so this was happening in 1989, which is great. And we're doing the same thing in 2025, but much better. So here's some examples from folks at Stanford. That's what the expert data looks like. They have these things called UMI grippers, which are grippers with cameras on the wrist. And so they collect a bunch of data from like egocentric views. And then use that to like do imitation learning. And then you can use that on a robot to do things autonomously. Right? So on the left is data collection. On the right is autonomous execution. You can see it's still like kind of slow and still in a similar setting to training, but it is autonomous and it's reasonably long horizon. And you don't have to estimate what the state of the ketchup is, right? And so there's like nice advantages of this compared to like a model-based system. But yeah, I think this is pretty cool. You can see that it's reactive and it's closed loop and it'll repeat things, right? Which is nice. The nice part about this particular demo is that the data collection process is also pretty easy. You just wear these gloves and do things. But it's nice. Alrighty. So that's behavior cloning. Does that make sense? Pretend that imitation learning is inherently a sequential problem, is a supervised learning problem, right? So image classification is typically a one-step problem. What we're going to do is we're going to convert an imitation like a policy learning problem into a one-step like classification or regression problem and just run supervised learning on it. Right. So like what could go wrong? Is this going to go forever? But what could go wrong with this process? Right. So we've talked about imitation learning. It seems like it kind of works. So what could go wrong? But if you're out of this. That's right. That's right. Exactly. So the tricky part about imitation learning is that imitation learning pretends that learning policies is supervised learning and it's IID, but acting in the world is not IID. Like your decisions now will affect your decisions later, which will affect your decisions later, right? And so you have this issue of compounding error, like Siddharth was saying, it's about when you go out of distribution. So let's say you started at the first state, right? And then you made like a little error, a tiny little error, and that's fine normally. If you are truly IID, it's fine. Every model has some errors. But what's happening now is you're acting sequentially. And so you made a little error, and then you landed up a little bit out of distribution. But I've never seen any actions at this state. I've only seen actions at this state. And so now I'm going to make a little bit of a bigger error. And then I'm like more out of distribution. I'm going to make a little bit of a bigger error, right? And so your error compounds over time. And so you get this kind of like out of distribution problem where you like drift away from your training trajectories. So even in the training states, you drift away from your training trajectories. And so this really stems from the fact that imitation learning pretends that it's a supervised learning problem when it's really not, right? So it's like you learn your policy this way, you pretend that is a one-step problem, but then you evaluate your policy not as a one-step problem. You evaluate it by running your policy in closed loop. You run it, you take the next state, you feed it back in, you take the next state, you feed it back in, right? And so there's this like fundamental mismatch between what's on the left and what's on the right. Right? So on the left is like a one-step problem, and on the right is what you actually run, is you run your policy in the world. And that is not the same thing as pretending that, you know, everything was a one-step prediction problem. Hence, you get these compounding errors where you make a little mistake, a bigger mistake, a bigger mistake, a bigger mistake, and so on. And that's why, like, if you look at this example, it's like very, very close to the training set. And you have a lot of data, but if you go anywhere outside of that, it gets kind of hard to recover. Okay. And if you see this in like, this is not just a conceptual issue. You look at like what's happening on the Alvin too, you see that it's like drifting and gets out of distribution easily. And so you wouldn't run an autonomous car with behavior cloning in most cases. Okay. So is all hope lost, right? We've said it's compounding error, but we invested hundreds of millions of dollars. So how are we going to deal with this? Any ideas? We have this problem of like drifting away from the training distribution, right? Even if you make little bits of errors, you drift away. How could we fix this? Exactly. But we'll work up to that solution. But one thing I thought was kind of cool was this video from NVIDIA back in 2016. And so they drove their autonomous car using like a version of behavior cloning. And they actually drove it for like quite a long time autonomously. Yes, with a safety driver and everything. But this is what the system was looking like initially. As you can see, it's running over cones and doing crazy stuff. Right, so this is what behavior cloning does. Right. This is what behavior cloning does. Let's see. So you wouldn't trust a car like this to be deployed, right? But they made some changes, and it's not just more data, but they made some conceptual changes. And that kind of led to behavior that looks like this. And so you can see that it's a lot smoother, doesn't have these drifting errors. Apparently, this person is confident enough to pull out their phone. But it seems to perform a lot better generally. It has less of this like drifting and like swerving behavior. All right. So I thought the change they made was super, super clever. And so what they did is they said that normally you would collect one image and then you would have like an action. Did I go left? Did I go right? How much I turn my steering wheel? But what they did is instead of having one camera, they had three cameras. So they had one to the front, one a little bit to the left, one a little bit to the right. And what they did then is that they labeled the front camera as usual, but they labeled the left camera as going to the right and the right camera is going to the left, right? And so you can see that it's kind of essentially suggesting that you have three views, right? So your car has three views, one like this, one like this, one like this. And so this is like the usual thing. But they have like data augmentation, which says, hey, if your car had been facing to the left, you should probably go to the right. If your car had been facing to the right, you should probably go to the left, right? And so essentially what's happening is that if the car had drifted off, they like know how to correct for it. And so it doesn't let the car drift off like crazy. Essentially what it does, it forms like a tube around your like optimal data, which like always brings you back, right? And so in this particular case of autonomous driving, they like created a tube that brings you back to the optimal without having to collect more data, just with a clever data augmentation trick. So I think that was pretty cool. But the general principle here is that whenever you have this kind of compounding error, you want to be able to like correct back to the optimal. Right? You want to recover back to the optimal, as Clea has been looking at as well. And so like the goal is you want to go from things that are out of distribution back to being in distribution, right? And you want to kind of come back to things that you know. And so essentially the key idea is you want corrective labels that bring you back to the data, right? And so there's a bunch of different variants of this, but you want things that essentially, if you're drifting, let's say you had like something that is drifting like this, you want things that like bring you back to the data, bring you back to what you know, right? And so that kind of will inform the design of the rest of our algorithm, right? The point is we have this sequential compounding error, but when you go out of distribution, you just want to be able to come back in distribution as quickly as you can, right? And then you don't drift and swerve and have all these problems. Okay. Does that make sense? If you have a sequential problem, you make little mistakes, they get bigger and bigger and bigger. But if you find a way to come back to your data once you've made these mistakes, then you don't have compounding error over your horizon. And so behavior cloning normally has a complexity of 8 squared, which means that it gets worse at a quadratic rate in terms of horizon. And if you do these fixes, you can show that it like is linear. So it's like a lot better. Alrighty. So how do we get there? Right? The key idea that drives a lot of these algorithms is that you want to kind of try to make your training distribution as similar as possible to your test. And so what the reason we had this mismatch, right, was that we like had our training distribution under like we had like states and actions which were drawn from pi star, and then we like optimized pi theta, right? But then when you execute your policy, it states and actions under pi theta, and you measure whatever. And so the mismatch is that the training data was under pi star, and the testing was under pi theta, right? And so train is not equal to test. And in machine learning, if train is not equal to test, you're just screwed, right? And so the key idea in this next method, which was called dagger, was just try to make train as similar as test, kind of using this idea of like correcting back, right? And so essentially what dagger does is it tries to make your training data much closer to the evaluation setting. Right? And so the idea is pretty simple. It says that rather than trying to be pretty clever with p pi theta, we just like increase our training data cleverly. Right? And so the way it works is that it's an algorithm called Dagger, or data set aggregation. And the way that Dagger works is that you start by collecting training data from like, so you start by like collecting data from your expert, right? So your expert gave you S's and A's from some pi star. Okay. Then given these S's and A's, you run behavior cloning. Behavior cloning gives you your best policy pi theta. Right? And then what you're going to do is you're going to run pi theta in the world. Right? So pi theta is going to make mistakes, but you're going to run pi theta in the world. So let's say this was, sorry. Let's say this was your expert, right? You like did behavior cloning, you ran pi theta, it gave you this trajectory, right? Drifted. Then what you're going to do is you're going to ask an expert to label what the optimal actions were in each of these states. And so the expert is going to say, at this state, you should have gone here, 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 right? And then you're going to take these states and actions, you're going to add them to your training data set. And then you're going to repeat. So it's called data set aggregation because you just repeat this process of running your policy, labeling it with an expert, and then repeating, right? And so the overall algorithm looks something like this. You're going to run pi theta. So you're going to run behavior cloning first. You'll get pi theta. You'll run pi theta forward in the world, right? You'll run it closed loop. So you'll run it, you get observations, you'll run it, you get observations, you'll run it, you get observation. And then so that can be suboptimal. But what you're going to do is you're going to ask a human to kind of label the states that you visited with optimal actions. You're going to add that data set of like, the states that you visited with actions labeled by an expert back to your data set, and then you're going to repeat. So it's going to start with basically this, It's going to make some mistakes here. You're going to like add expert data here. Now this whole thing is your training data set. Now let's say it makes a different mistake here the next time. You're going to add the expert here. And now this whole thing is going to be your training data set. It's essentially like a computational version of whack-a-mole. You're just going to like whack-a-mole all the issues, right? So you're going to say like, you're going to do behavior cloning. You're going to see where it makes mistakes. You're going to have the expert label how to act optimally there. And then add that to your data set, repeat, repeat, repeat until you don't make any mistakes anymore. Right? And you can show that that converges to the optimal policy in the limit. Okay, so this algorithm is super duper simple. That's why it's very popular. But it's essentially run BC, run your policy, relabel with a human expert, aggregate, repeat. Any questions? Makes sense? Yeah. Yeah, you just keep looping it. So you like start with just behavior cloning, and then you like do this one time, you increase your data set, you make mistakes again, you increase your data set, you make mistakes again. Repeat. All right. Oh, there you go. And this actually kind of works, right? So this is an example from Ross and Bagnall in at CMU, where they're trying to like navigate with a drone around forest trails. And so they show that like you're able to kind of learn behavior that can go for like several minutes through these dense forest trails just by using this dagger type approach. So they have like a safety driver who like provides corrections when you're drifting off, and that kind of gets aggregated with your data set, and then you repeat. Right? And so you're able to react to untrained obstacles and so on. But yeah, it does work in practice. But let's try to think about what makes this hard, right? If you look at this approach by itself, what makes it hard is that you're asking a human to label this thing with actions AT on states that the robot visited in hindsight, right? So you're saying like, I'm going to run the policy. This is the expert. I'm going to run my policy. And then I'm going to ask the human, what would you have done here? 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 Which is kind of a weird thing to do, right? Like if I like showed you a picture and asked you, how would you like drive a car? It's like not super obvious, right? Like it's not intuitive, right? And so one of the issues is that you're doing things in hindsight, right? And the other issue is you still need a human in there all the time to provide you all of these corrections. So it's expensive, right? And we're trying to save money. And so it's the human is the problem. And then it's the fact that the buy has to be labeled after the fact, right? And so if we want to make these algorithms practical, like those are two big issues. Okay, so our two issues are labeling in hindsight, and human. All right. How would we fix these issues? Let's just start with the first one, right? So it's like the general intuition here is that if you make mistakes, you like want to be able to correct back to the training data, right? Now, if you wanted to avoid in hindsight, what do you do? Exactly, exactly. So what you end up doing is you kind of do the corrections at data collection time, like you're just saying, right? So it's there's an algorithm called DART, which came out of Berkeley in 2017. But basically DART is super duper easy. It just says that when you're collecting training data, to add a bit of noise to your data collection, which means that if your expert says A, execute A prime, right? And so your expert is going to tell you to go here. You're instead going to go a little bit off here to A prime, right? So expert says A, go to A prime, where A prime is equal to A plus some epsilon, where epsilon is sampled from some Gaussian, right? And so saying that like, don't quite listen to the expert, make small errors, right? But then the reason to do this is because when the expert sees that I've gone here, it will like the expert will automatically correct to bring you back, right? So the expert is kind of forced to do corrective action. And so it forms like a tube around the optimal just through data collection, right? So you obviously, if you add too much noise, then this becomes an uncontrollable system, right? So then you like start doing crazy shit. But if you add a small amount of noise, you can show that like an expert will automatically serve as a corrector for you without having to do anything in hindsight. And so this whole paper, which you guys should go and read, is essentially just trying to formulate something like this, where you're trying to maximize likelihood, but you're trying to add some noise to the training data during data collection. And the whole, the fancy math in the paper is just trying to choose how much noise to add. But in practice, you just add a small amount of noise, and it really, really helps with performance, right? So like almost every production system will have a small amount of noise added in, which is counterintuitive because like you make things less accurate, but they help a lot with like recovery and like demonstrating recovery behavior. And then you can do things like just have a, okay, no video here. Oh, video. But you can do things like making a bed and so on with this kind of method. Right? So the point was they just collected data with a little bit of noise. And at test time, even under like slightly different conditions, this bed was never made the same way. It's still able to recover and do pretty well for long horizon flow. Okay, so that's our first solution, right? We're gonna collect data. We're gonna collect corrective data during training time. And so let's recap what we've done. With behavior cloning, which is supervised learning has drift. Dagger corrects for the drift by like just aggregating more data, but it needs to do it at training time and it needs a human. We've collected, it has to do it in hindsight and needs human. We've removed the hindsight problem, right? And so that's better. The next thing we're going to think about is we need to kind of get rid of this like requirement for a human, which is expensive, right? So for instance, you're like doing a task like this on the right. This is from our lab here. But you're trying to like manipulate things with chopsticks. And if you have like your robot jittering when you're manipulating things with chopsticks or you're doing surgery, it's going to lead to some bad outcomes, some negative $100 million outcomes. And so we don't want that kind of thing. And so the assumption in Dart, those kinds of methods, was that you can actually perform corrective behaviors when you have noise. But in certain cases, we have to be extremely precise. You can't actually do that, right? So if you're trying to pick things up with chopsticks, but your chopsticks are like shaking, you can't really perform the corrective action that you're looking for. And so we need a different solution. And so that kind of brings us to this idea of generating corrective labels automatically. Right. And so this is some work from my group. But the idea we're trying to think about is how do we find corrective labels that bring you back to the data, but without a human, right? So I want to get rid of the human, and I want to find a way to like bring these corrective labels that bring you back to the data, without actually requiring a human, right? And the key idea that we're going to use is that you don't need a human to get you back to the training data. If you know how the world works, you know the dynamics of the world, you can follow the dynamics of the world to get you back, right? So the dynamics of the world tells you if you fed in some state and action, what is the next state, right? And so if you knew this, you could solve an optimization problem, and that optimization problem would tell you how to correct your behavior. And so that's the key idea behind this next thing, which we call CCIL. But CCIL basically just says, if you want to like find ways to correct your behavior, you can either use a human, or if you had a model of the world, you can just solve through the model of the world. As the model of the world tells you how the world works. And if you know how the world works, then you know that if you were here, if you fed in this action, you would come back here. If you knew that if you're here, you fed in this action, you would come back here, right? And so you can kind of get the same effect of a human if you just knew the model of the world. And so you can kind of augment your data set with states and actions that bring you back to the training data, by just trying to find a state and action, which like brings you back to something in the training data when you put it through the model of the world map, right? So if you knew a world model, then you can go through your world model. It takes you from states and actions back to your expert data. And so essentially, if you drift off, like these states and actions will bring you back to your expert data. Right? But you don't need a human to do that. You can just get that from a model. Yeah. Okay, so so this seems great, right? Easy, no human, all wonderful. What's the problem with this? Right. You don't have a model. Like the problem is you don't have a model, right? We've been talking about a setting where you just get training data. Where do you get the model from, right? And so the first thing that we do is we try to learn a model. So you have data from the world, you have data of states, states, actions, and next states, right? You can try to learn an approximate model of the world that tries to like minimize something like this. right? And so it tries to find the best approximation that explains how S and A transition to some S prime, right? So it's like you learn a model from data. And then you can use your learned model in place of, you can use your learned model in place of your true model, right? So you don't know the true model. You don't have a model of the world, but you can use your training data to learn a model F and then come back to the data using your learned model F. So that's great, but what's the problem with that?
Yes, you don't know if you can trust your learning model.
You don't know if you
Say
can
that
trust
you
your
can
learned
trust
model.
it.
Exactly.
Yeah.
Exactly. Right. So you don't know if you can trust your model. So it depends where you train your model, right? And so in most cases, your model is only accurate in some narrow region around your training data. And so you can't actually trust your model to be good everywhere, right? And so what this paper kind of tries to do, it says that your model can't be trusted everywhere, but it can be trusted in some small region around your training data if you like impose a few constraints on it. Right? So you can say that like you learned a model, F hat. You can find things that bring you back to your training data, but only in places where your model can be trusted, right? And your model can only be trusted in neighborhood around your training data if you like force your model to be smooth. And so what this thing does is just says like, let's try to come back to our training data using your learned model, but you can only trust your model in a small region. And so you say like, let's learn a model that's smooth and only trust it in a small region to come back. And so I will never generate a label that goes from here to here because I can't trust my model there, right? And so we're going to learn a model, we're going to force it to be smooth, and then we're only going to generate corrective labels in a small region around the optimal training data. But even that will lead to a big difference in performance. Yeah. Okay, so last 2 minutes, let's kind of skip to some videos. We had this task of putting some coins into a piggy bank. This is what happens without corrective labels. You'll see like a little bit of drift. No? Oh, no, that's with corrective labels. Okay, good. With corrective labels, you're able to do it successfully, but without corrective labels, you'll see a little bit of drift that leads to the starboard. And so for these really high precision problems, you can kind of get some like corrective behavior that lets you be accurate for disturbances. If you want, you can go play with it in the lab. It actually works. Here's some other examples. So picking up a cube, which is like a couple millimeters, and playing with some Legos, picking up a coin. All of these seem to do really well with this kind of corrective behavior. The nice thing is you don't actually need any human interventions or dagger. You're just doing this with a model, right? So you're just learning a model, and in a small region around your training data, you're correcting back to your training data, and then you're just repeating, right? But without the corrective labels, you see that it leads to some failures. I might have cherry picked these, but you get the point. Okay, so that doesn't solve all the issues in imitation, but we'll have to talk about the rest of them next week. So, Wednesday we'll do the discussion and guest lecture on Friday. I'll send out some details. All right, see you guys.
Thank you.
Thanks.